We have another board hidden. All right. Good morning, everyone. So, where we were left? Well, we went through the introduction of GR, what we need, the key ingredients we need. We gave a look at the lambda CDM model, and we look at the materials, or let's say the stuff that is composing the universe. So we have matter, radiation, and we decomposed matter in two components, relativistic and non-relativistic. We are going to have baryons, and dark matter as a non-relativistic species, and photons and neutrinos as relativistic species. That's for the matter components. Then, on top of that, we realize the fact that to explain the acceleration, or we invoke the cosmological constant, which is something, if you wish, belongs to the geometrical sector, right, in the Einstein field equation. So you have your Einstein tensor plus the cosmological constant equal to the energy momentum tensor, which is composed by the stuff that we kind of know, plus dark matter, okay? So we're going to have the matter component and radiation on the left-hand side of the Einstein field equations. Then we need to explain the nature of the cosmological constant in terms of something more fundamental, for giving a link to particle physics, and what we did was to get basically the Einstein field equations. So we have G mu nu minus, then we have the cosmological constant G mu nu equal to T mu nu. What we are going to do is to bring it on the other side of the equation. To construct then a term referring to the cosmological constants, but associated to an energy momentum tensor component, therefore to stuff, okay? So an energy component, energy momentum component of our universe, which is associated to the vacuum energy, okay? Where is this coming about? Well, we bring the cosmological constant on the other side, and then what we are going, well, there is a constant, so there is an 8 pi g over c to the power of cos, 4 t mu here, okay? So we bring these terms on the other side, such that we have our Einstein tensor equal to 8 pi g over c to the power of 4. So you see we are basically collecting all the terms together here, times the energy momentum tensor, which can be associated to radiation, matter, and all of that. And yeah, there's the plus, therefore plus something that we are going to associate to the cosmological constant in terms of an energy momentum tensor. Okay? Energy momentum tensor, which reads like C4 lambda over 8 pi g mu. So basically, these are all terms that are going to cancel the g mu nu, which is here, and the prefactors that we placed in front of it. Okay? What's that? That's an energy momentum tensor. And what we could do is to give an effective description of this energy momentum tensor in terms of a perfect fluid. Okay? As a perfect fluid. So lambda as a perfect fluid. And therefore, what we're going to do is to sort of impose this sort of structure of a perfect fluid, of the energy momentum tensor of a perfect fluid, to what we derived in this way. Okay? So we have our energy momentum tensor T mu nu for the cosmological constant. So that's equal to C to the power of 4 lambda 8 pi g, g mu nu. And now we make this imposition. Okay? We say we want this guy to be of the form of a perfect fluid. Therefore we have T over P rho plus P, the pressure divided C squared, U mu, U nu, plus the component again associated to pressure multiplied times, which is scaling the metric components. Okay? So how do we get these two things here? Do you see any relationship with respect to the forward velocity of the observer? No, there is not. And therefore, this term must be equal to 0. Tuck. Okay, this is gone. We have lost this contribution from this side. What's the consequence? Well, this means that basically rho plus P over C squared is equal to 0. That's an equation of state. That's an equation of state because an equation of state is an equation, given a fluid, which relates pressure to density. That's the equation of state associated to the vacuum energy that we are going to associate to the vacuum energy. Sorry, to the cosmological constant. Then I will come to the fact that we call it the vacuum energy. Okay, therefore we're going to have the pressure, which is equal to -1 times rho C squared. Why am I stressing this -1? Because we have seen, also for the other components of our universe, that we can have a parametric equation of state, which is generic, W equal to 0 for dust, for matter which has no pressure component, W equal to -1 for the relativistic species, neutrinos and radiation, and in this case, we find basically an equation of state parameter associated for our lambda, our cosmological constant, which is equal to -1. Absolutely weird. Okay? The other case, we had 0 or 1/3. That's is a positive number. Here we have something which is negative. So we have a negative pressure. So we have a certain density, there is the minus, and this gives a negative pressure. And therefore, in GR, if we go back to this sort of representation, we understand that this is kind of a contribution of a repulsive force. Okay? So if you think in terms of gravity as two fundamental constants, G and lambda, this theory written in this way tells you that there is an attractive contribution on small scales and a repulsive contribution on large scales. So that's how gravity would work. Okay? If you bring it on the other side, you change the way of thinking, same physical representation, same observables that you would obtain, but you think in terms of this specific fluid. It's an ideal fluid which has that specific equation of state parameter. Okay? Continuing along this line, if this is equal to 0, we are left with that, right? Therefore, we have P, and then we have G mu mu. Somebody's calling. No thanks. Okay. Okay, so that's equal to 0, we are left with that. But now we also have the equation of state. And therefore, we have a relationship between the pressure and the density. And what we can do is to plug in our pressure down there. And we are going to identify the density associated to the cosmological constant. So it's going to be minus rho C squared G mu. Okay? And if we look at the other side, we have G mu nu, and you find rho C squared and these constants here. therefore you obtain that your cosmological, the density associated with the cosmological constant, thinking at it as an ideal fluid, is equal to c to the power of 2, because we have c squared, c to the power of 4 that cancel out, and then we have the 8 pi g. Yeah? Where, sorry?
Because there's minus on the row at the bottom.
Yeah?
Yeah. So if you set those two equations equal, will that move one bottom?
Ah, yeah, sorry. Read it. Rho, t più nu. Oh, stupid minus. This should be plus. This should be plus. So I've lost it here somewhere. Okay. Anyway, that's the line of thought. Okay. So we arrived at identifying the cosmological constant with an ideal fluid with this equation of state parameter and a density of this sort. Okay. Good. Now there is a problem here. Yeah.
Maybe because usually people define G as lambda instead of minus.
Yeah, basically. But yeah. Okay. Good. Okay. Moving forward, there is a problem here because we are, if we want to go to a fundamental, to associate to fundamental physics, what we are going to try to do is to explain this energy momentum contribution in terms of something that do not depend on the state of motion of the observer. Okay, there is no dependency on the u mu components. So it doesn't depend on the observer. Plus, the other thing is that lambda is a constant. Okay? So in the Einstein field equation, here we have our Riemann, we have our tensor R mu nu minus 1/2 R G mu nu. Okay? Where we have our Ricci scalar. So we have the Ricci tensor, the Ricci scalar. But keep in mind that these two things are extremely different with respect to each other. These are both scalars, but this one has a dependency on derivatives, double derivatives of the metric. Okay? That's very different with respect to this guy. This is a number, fixed, constant. Okay? So no dependency with respect to the motion of the observer. This guy is constant, no matter what the universe is expanding or contracting or whatever it's doing, in contrast to all the other contribution of our universe. And we conclude that this guy should be associated to the vacuum energy. These are the two key characteristics of vacuum. Okay? Which is not nothing. Vacuum can have, not always, but can have a energy density contribution, because we know that we're talking about in fundamental physics. Quantum mechanics is there, okay, and therefore we can have a scatter, random scatter with respect to the zero level of the energy, and this gives you a net contribution of the energy density, unless there are symmetries that basically cancel out these contributions, and lambda effectively is equal to 0. Okay, should be equal to 0. Okay, which is the path that we are going to follow in the next lectures, because if lambda is different than 0, there is a conflict with the prediction, well, actually with the prediction, with the measurements that we do of our universe, because we can measure the expansion of the universe and all of that. We have a number for lambda. And this number is in conflict with what would be predicted if there would be no symmetries to set this guy equal to 0. Okay? by several orders of magnitudes. Okay? Therefore, what we are going to do in the next lectures, I mean, I'm going to show you a little bit this part, is going to say lambda is equal to 0, but then we have a problem. So we fixed the problem with the particle physics, but we have a problem. The universe is expanding in an accelerated way. Therefore, what we need to do is to invoke something else that provides this acceleration. And that's going to be dark energy. Okay? That's why the ingredients of the universe are going to be matter, are going to be radiation. So we are going to have like neutrinos, we are going to have dark matter, and we are going to have the baryons. And then, so then radiation, and then a scalar field that we are going to discuss in quite some detail. Yeah?
Are there more accurate and more reliable measurements of the vacuum energy that lead us to think that the cosmological constant must be one that have to be modified? Why not look for
Both? Or
just the vacuum energy? You said we have a...
because now I'm going to do some order of magnitudes evaluation of what is expected, the energy that you would expect for the vacuum, and we will get a number which is much, much larger with respect to what we get with cosmology. Okay, and you cannot reconcile the two things together. So there is a conflict between the numbers, okay? And therefore,
the dark energy would set this.
no, then what you would do is that, so basically from the particle point of view, what you do is to say, okay, I have like in supersymmetry theories, then this guy will be equal to 0. There are symmetries that basically set this guy equal to 0. This is gone, okay? And then you need to invoke an additional fluid, so it is dark energy, so, to explain the expansion of the universe.
The cosmological constant is also in conflict with both the vacuum energy different than 0 predicted by the standard model and with the supersymmetry theory.
The two things are completely, from an observational point of view, if you wish, of what we perceive of the universe, the two things are completely degenerate. Because if we think in terms of an action, okay, because that's the thing that describes our system, so our universe, we are going to have our four-dimensional invariant volume integration, so we're integrating over a volume. So just to be more explicit, that's the integration over the 4 dimension. This guy makes the 4 volume invariant. And then we have the Ricci tensor, and in case we would have the cosmological constant contribution. Okay? And then if there is matter, we are going to have the contribution of the action given to the action given by matter. Okay? But look what we have here. So here I'm basically using the Hilbert, the Einstein-Hilbert-Lagrangian, which is R minus the square root of minus G. Okay? That's standard GR, plus the cosmological constant. Now look, we just have this function here. So nothing forbids us to remove this guy and change it here. Okay? Nothing forbids us to get rid of this one and modify gravity. Okay? So you can explain the expansion of the universe in several ways.
But we don't have alternative theories on the vacuum energy.
From a particle point of view? Yeah, I mean, you have an estimation of the vacuum energy. You have it. I'm going to do it like an order of magnitude estimation. So this you have it. Which is in conflict with the number that we had from the cosmological expansion that we observe. I'm going to show it now. Okay? So the way to solve it, well, I'm basically going to do this short order of magnitude derivation. Okay? But you understand here, I mean, I wanted to arrive here later, but since you're pushing me, so you understand that you have freedom to build up theories that are different in nature to explain the expansion of the universe, and they are completely degenerate one with respect to each other. Okay? To distinguish, they're indistinguishable, completely identical predictions. Okay? You can start to distinguish, for example, modified gravity with respect to standard GR plus cosmological constant or the dark energy and so on, if you have more fundamental theories, not an effective theory like a GR, and all the theories that are based on geometry, such as GR, but they are like quantum gravity. Then there are predictions that differ from what you would get from GR. And then you can distinguish a quantum gravity theory modifications with respect to dark energy or these sort of things. But at this level, they are completely degenerate. I'm going to show you this in more details later on. So, okay, so let's give a look at the problems. So that's problem 1, which is the value. That's the actual value of the cosmological constant that can be measured from cosmological observations. That's why actually this guy popped up. So we take our Friedman equations that link our Hubble function 8 to 8 pi g over 3 rho minus k over 8 to the power of 2 plus lambda over 3. Okay, just Friedman equations. So curvature equal to 0, so we can, for example, forget about that. But anyway, it's going to be negligible in any case because we are anyway very close to flat geometry. For this guy, we can forget about it. We have a density contribution that for this sort of order of magnitude evaluation, we can forget about. Okay? Therefore, we have basically see that as an order of magnitude, the cosmological constant has to be of the order nowadays, okay? Doesn't matter which epoch we are going to consider because this guy is constant, and therefore we can use h today, okay? And we would have a measurement of our lambda. And this guy we know to be roughly 70 kilometers per second per megaparsec. Okay? So what we can do? We have our number, so this becomes our h0 0, so we have basically everything evaluated at time 0, and we can get our rho. Therefore, rho, which is now only about lambda, because that's what is left. You can also think that we can place ourselves in the future, okay? It doesn't matter where these contributions are completely gone. Anyway, sticking to that, we have that our rho, now we are only considering lambda, again, as an order of magnitude estimation, that's going to be equal to 8 pi g. Okay? We can then express g in terms with respect to the Planck mass. So there is just a relationship between the Planck mass and the value of g, c square lambda, mp squared over 8 pi h bar c, c squared. Okay? So that's what we get. So g is this guy here. Okay? And we are left with lambda m mass Planck squared over 8 pi h bar squared. Why I did this? Because now we can easily express in terms of an energy, and it's roughly 10 to the minus 47 giga electron volts, power of 4. Okay? A crazy small number. Okay? Completely off from all the other energy scales that we have in the other theories of gravity. To give you an idea of how small this guy is, okay, we can think about of a photon. Let's think at a photon with a certain wavelength. Okay? And let's think at the weakest photon, the photon with the lowest energy that we can possibly think of. What would be the lambda that we can think of? The Hubble radius. Okay? I'm not saying that such a photon can be produced, okay? But let's think that such a photon exists, and the wavelength is the largest that we can possibly think of, the one of the Hubble radius. within which, so within an horizon, we can have a coherent structure such as a wavelength, okay? Outside we lose the casual contact and therefore all is sort of lost. Okay, so let's get that, which is roughly 3 gigaparsec over h. So that's a crazy large number. And if we look at the energy that corresponds to this photon, that's what we will get, and we have an energy of 10 to the minus 29 electron volts. So order of magnitudes more energetic than this guy. Okay, this is a crazy small number, completely off from anything that we can think of. If we now start from the particle perspective, so from this we conclude crazy small. Crazy small. Okay? Then we can start to think about the fluctuations of the energy density, which are going to be associated to a frequency associated to the energy with a factor of 2, which is 1/2 square root k squared plus m squared. Okay? Then if you want to know the total energy that is going to be associated to our vacuum, then we need to integrate with respect to all the k values that are allowed. Okay? So we basically make an integral in the phase space between 0 and in principle some k max. Okay? We need to have a truncation to the maximum frequency, otherwise the number blows. So we are going to make our integral in the k space, so in the momentum space, 2k to the power of 3, and then we have our contribution associated to each k. And therefore we have 1/2 square root of k squared plus m squared. Okay? Nice. To simplify our life, again we think in terms of isotropy, therefore we can integrate in shells of energy. So basically we are going to use polar coordinates. And therefore we are going to have an integral, again between 0 and k max. And then we have 4 pi k squared dk over 2 pi to the power of 3. And again, 1/2 square root of k squared plus m squared. Okay? Polar coordinates, we are integrated in shells of energy. Okay? So this would be like k1, k2, a certain k, so an absolute value k for our associated to our momentum, is going to be a shell in energy. This k or this k has exactly the same energy, okay, because of isotropy. Then what we can do is to assume that the contribution given by the mass is much smaller with respect to the one of the momentum, okay, for simplicity. And what we end up with, so we are kind of conservative in the sense that we are forgetting about the 0 level, okay? Therefore the number can only be larger. And the integral, therefore, becomes just a set of constants, so just the integral, but again 0 and k max. Then you have the 4 pi, the 2 pi squared, you know, all these terms kind of cancel out. You're left to k to the power of 3 dk over 2 pi in the k. Just an integral with respect to k. And this gives us a k squared max over 60 pi to the power of 2. Okay? What is this k max? It is kind of open, okay? But we can set a limit, for example, which is given by GR, because we know that GR is valid down to quantum, is a deterministic theory. It has nothing to do with quantum mechanics, and basically the theory breaks when quantum mechanical effects are in place. Okay? When we cannot neglect them anymore, GR is broken. Therefore, what we could do is to look what is the largest k that we can possibly assume and use for these derivations. which are based on GR. That's coming from GR. So we stop where GR arrives. And we arrive at the conclusion, which is basically, we arrive at scales that are the Planck length. Okay, and then we need quantum mechanics. And the number that we would basically get is 10 giga electron volt, and the power here is 74. 10 to the power of 74 with respect of 10 to the power of minus 47. These are whole hundreds of magnitude of difference, okay? Here we could have been here losing time doing super finite and sophisticated computations to get the exact number, the very precise number, but you know, you change by a factor of 2, 3, 10, 100, 1,000, but we are talking about 100 orders of magnitude of difference, okay? A very strong conflict between the two interpretations of the same phenomenon. That's not over, because this is one problem, but we have another problem. This is fixed. Which is the coincidence problem. And the problem consists on the fact that the energy density associated to the cosmological constant is roughly 0.7. The one that is associated to matter, nowadays matter is relevant, radiation is not, is roughly 0.3. And these two numbers are order 1. That's the same stuff. Why? Why now one is not 100 times larger with respect to the other? Why not 1,000? Okay? Why is now, when we are living in this very moment, they have the very same number? Why so specific? What is this coincidence problem coming from? Okay? To show you how strict is this problem, we can give a look at estimate the time at which this is happening and how tight is the range in times for which this is happening. Okay, because you know, if this would be kind of extended for extremely long time, then okay, it's likely that we are just at that value because it's basically kind of always at this value, okay, or for a very long time, but actually that's not. So we can evaluate for the coincidence time. Which is the one at which the energy density, the density contrast of the cosmological constant is equal to the one of matter. So when the poof, perfect equality basically happens. And we know how matter is scaling as a function of density and therefore as a function of redshift. Therefore we have these scales as a to the power of minus 3. So the density we know that goes down as a to the power minus power of minus 3. Which in terms of redshift is goes to the power of 3, not minus 3, because it's the inverse, it goes as the inverse of the scale function. And that's the time, the redshift, where this is happening. Okay? And that's roughly 0.3. So then what we can do is just to isolate our redshift for ZC is equal to omega lambda over omega lambda minus 1 to the 1/3, and that's roughly 0.3, which is today. Okay, we are at Z0, which with respect to redshift 1000, which is the radiation domination, we are basically, this is today. Okay? To look how tight is the narrow range, we can look what is the variation, the energy density with respect to ln A. Okay? And the cosmological constant is constant, but not the density contrast, because it's the density of the cosmological constant divided the background density. Okay? But actually, with respect to the critical density, and the critical density is different at different times. Therefore, there is an evolution there. And this guy, if we take now log 10a, okay, so that's the past, that's the future, so that's redshift 0, redshift infinity, the way around. This is the plot for how omega lambda is changing as a function of time, and if you plot it, that would be the 0, would be something like that, super sharp function, okay? So here is roughly 10, just to give you an idea of the width. Well, actually, this is already very large, so let's set it as roughly -5, okay? So it's very, very tight, and this is happening today. Why? That's a problem. So, what we can do is then to try to cope with these problems, because we don't like coincidence, so we don't like fine-tunings. Why the value of lambda is so small but not 0? Why is that? There is a conflict also with particle physics. We can solve it if we get rid of lambda. Okay? Problem that lambda has, again here, why that value is telling us that today there is this value. So the idea is to say, okay, lambda is equal to 0, so we can use supersymmetry theories that tell us that the vacuum energy is 0 because of some symmetry, there is track cancellations, and that the energy level is 0, which would allow us to do that. We are consistent, but then we need to explain the expansion history of the universe. And therefore, we invoke dark energy, an additional fluid that enters in Einstein field equations that is responsible for the accelerated expansion of the universe. Okay? Now, do we solve all problems? This one is still affecting dark energy. So with dark energy, we solve the problem 1, okay? But the coincidence problem is kind of still there, okay? So we are going to see that we can alleviate this problem or solve it completely with dark energy if we build up some model that predicts or that sort of behavior for the values of our omega lambda nowadays, no? The coincidence problem. So, dark energy, which is fluid. I'm going to try also more complicated stuff, like tensorial theories and stuff. I will leave them aside. No need for that. We're going to focus on dark energy as a fluid, which is called quintessence. Okay? And problem 1, fine-tuning is gone, because lambda is equal to 0. We don't need to tune anything specific. Problem 2, we need to take care. We need to take care because what we need to build up are models. For example, they're called scaling models, where by construction of the theory, omega associated to dark energy now, I will not call it anymore lambda, now dark energy, with respect to omega matter is roughly constant. And therefore, it has always been like that. It's not a specific case that we have this problem, so sorry, these two values, where are they? These two values that are roughly the same, but it has always been like that. Okay? Or very rapidly the system evolves to a situation in this is the case. Okay? Other ways other ways to solve this problem are called tracker solution. in which the model, the universe, the system, evolves naturally in the direction of having the two energies to be the same. So we have omega dark energy that tends to omega matter. Okay? It naturally evolves in that direction. Okay? As I already mentioned the other time, using dark energy, one of the various theories, is not the only viable solution, because we could invoke, for example, a non-homogeneous universe. Non-homogeneous universe. In which back reaction plays a role, okay? We build up all this theory assuming that the universe is homogeneous. We need to explain the acceleration with that stuff. But if we assume, okay, the universe might be not homogeneous, therefore we can not use that stuff and explain it through the distribution of the energy density across the universe, which is not anymore homogeneous, okay? I've already mentioned that in a previous lecture. Imagine that there is an overdensity here. That's the simplest one that we can think of. We are sitting here in a vacuum, so there is more matter in the surroundings with respect to where we are. And therefore, if we are observing galaxies in this direction, there is, with respect to the expansion, there is a net acceleration in this direction, because gravity is actually pulling in this direction, okay? The metric is such that it's naturally going that direction, right? It goes toward overdensities, not toward underdensity matters, attraction. And therefore, what if we take our spectrograph, we observe our beloved galaxies out there, we would see them redshifting in that way. Not only because of the expansion, but because they are also attracted by this overdensity. Okay? Problem is, we don't need to modify general relativity, we don't need dark energy, we don't need these weirdnesses, but we need to set ourselves very precisely in the middle of these voids. Because if we would be sitting here, we would observe an asymmetry with respect to the redshift in this direction and the redshift in the other direction. Okay? And therefore, yeah, not really likely. It's another coincidence, if you wish. We will solve a coincidence and introduce another one. The other one that I already mentioned is the entropic principle, in which we are basically observing that kind of behavior, this equality, just because it happens when the energy level of the universe is low enough to allow for molecules to bond and form complex stuff, such as life. Okay? I don't see a big problem with that, in the sense that I already told you, like nucleosynthesis now, energy levels are low enough, we can have the formation of heavier nuclei. Now it's just something happening now. So it's not that this is happening because we are special, but actually we are just one of the physics that is happening across the universe, just a bit more complex than the formation of heavier nuclei. Okay? And this is happening now because we are forming now, because this is from the theories. Basically, you get that the larger values of acceleration are more likely. But if these larger values of lambda are actually there, life or the energy scales would kind of decrease so low, so rapidly, because the expansion is so violent, that life doesn't have the time to form. Okay? Therefore, there is a cap, one that says lambda should be like larger values for the accelerations, for the presence of this lambda or dark energy, whatever, is going to be extremely large, is more likely, but there is a limit for the formation of life. And therefore, we are likely to be from here on, but not earlier. Because otherwise, structure formation would have not have the time to arrive at the level at which it is now. Okay? Therefore, more likely, less likely, possible, and we are sitting here. Okay? At the less likely acceleration, but which allows life. Coincidence problem solved. Okay? That's a way. that people is not satisfied with, because it's nicer to build up a theory that, you know, avoids that. But I mean, I would take also ourselves as a cosmological observable, okay? Like nucleosynthesis, I don't see much of a difference with respect to that, okay? Good, so I hit the 45 minutes. We can have a little break, and from now on, we will start to discuss dark energy. And I'm going to treat it as a fluid. After studying the various possibilities that are allowed within this framework, which kind of model we have, which kind of solutions are allowed, what are the predictions for the universe, its behavior and everything, we are going to look first for a fluid which is just self-interactive. No interaction with matter. Okay? The field interacts with itself, but not with matter. After having done that, we are going to, again, use a fluid, but now with an interaction. Okay? So there is going to be an interaction with matter. And here, I'm going to show you how you have to be super careful when you deal with baryons. Okay? In matter, we have baryons and dark matter. Okay? But if we are introducing an interaction with baryons, then we might screw up the entire rest of framework on which physics is built up. For example, the mass of an electron to be a constant. Okay? If you build up interactions with baryon, if you don't set up some screening mechanism, then you might have the mass of the electron is going to change as a function of time. What does it mean? That the lines are going to change as a function of lines of time. Okay? Therefore, the emission of hydrogen or the absorption of hydrogen is not going to be always at a certain frequency, but since the mass of the electron is different, it's going to be at different frequencies. And you misinterpret that as a redshift. Okay? Therefore, I'm going to show you how one has to take care of baryons. Because of that, if we want to stick to that, one needs to introduce some screening mechanism. Such that the interaction disappears if we have above a certain density level. Why it is solved the problem? Why not everywhere? Well, because we are observing, for example, galaxies. We are observing emission on the Earth, and these are over-dense regions. These are all over-dense regions. Therefore, we are going to look into mechanisms in which if there is an overdensity, because we are observing something within a galaxy, a supernova explosion or something, then the contribution, the coupling between baryons and dark energy is zero. And therefore, everything, all the physics that we are used to, you know, redshift measurements and all of that, is safe. Okay, we don't need to reinterpret everything. Okay, so screening mechanism. Then what we are going to do is to say, okay, let's play with modified gravity. With modified gravity. So we try to build up a Lagrangian in which we just have a geometric sector, like in GR. It's not going to be anymore like the Ricci scalar times the square root of minus determinant of the metric, right? The Einstein-Hilbert action, so it's going to be modified, but there is going to be the need only for matter, no need for dark energy. And we're going to see how we can build up frameworks that are completely degenerate, identical with respect to the one based on a fluid. Okay? I'm going to show you they are identical. You cannot distinguish one with respect to each other. Okay? And I'm going to show you how, if we are going to screw up gravity, if you wish, we can still recycle all what we learn about dark energy, about the cosmological expansion and all of that, so we can stick to what we used with dark energy and the cosmology that you all know, without redoing everything. Because you can get your equations that are built in the framework of modified gravity only matter into a one where you have GR, matter, and dark energy. Okay? Therefore, you can build up your modified gravity theory. You go back to it's called the Einstein frame, where you are just using Einstein GR, and make your interpretations and compare with data. Okay? And if you want to do the way around, you can go from here and get the equivalent modified gravity theory. Okay? So that's the games we are going to play with that. Okay? So now you're going to look at a self-interacting fluid as dark energy, and we're going to see how we can study the possible solutions that are allowed and how the universes that are produced within this framework can behave. Okay? Good. So we can have a break. We can resume at 15 past 12.
Can we fix the seminar thing? No.
Ah, well, we can. I will need the computer. Or do you have the document? Can you open it? Let me close the...